Okay, so in this example problem, we're going to be reviewing another hydrostatics problem, and specifically we're looking at this gate here, which blocks this reservoir from leaking over this ledge. And at a certain depth D, or at a certain height here in this left face, the gate will actually self-open in the sense that it will turn clockwise, kind of like this here, and water will be allowed to flow over the ledge like that. And what we want to do is determine the depth D at which the gate opens like that, at which the gate takes an angular acceleration. So before we hit that depth D, the hydrostatic pressure on this lower face exceeds the hydrostatic pressure on this upper face, and so the net moment is pushing the door, pushing the gate into this ledge. But eventually, as you fill this depth D on this left-hand side to a high enough level, the moment in the clockwise direction exceeds the moment in the counterclockwise direction, and the gate lifts off of this lip and self-opens as we described. So again, the task is to find the depth D at which this gate kind of self-opens and allows water to flow over this ledge. So here we have our gate as shown. We have our hinge on which the gate may move. We have water that is in the reservoir that is being blocked by the gate. We have our wall here and our lip, and this lip is what stops the gate from going further counterclockwise. And we have atmospheric pressure all around the outside of the problem. So on each side of the gate, on this face and this face, and over the free surface, it is the same uniform atmospheric pressure. And as you may expect, we have our gravitational field pointing downwards. Now, looking at the more specific measurements of the problem, this length here of this face is described as A. This depth, as we've already mentioned, is described as D. And we have our coordinate axes, x tilde and z tilde, as shown, originated at the hinge A. So to begin, our assumptions are: 1, we're going to deal with an incompressible and isothermal liquid, so water in this case. 2, we have a constant gravitational field. 3, the problem is static, just barely static, but still static. 4, we're going to neglect surface tension, so we're not going to determine the impact of any meniscuses or anything like that. And 5, we're going to neglect the thickness and the weight of the gate, which is going to be important in both the free body diagram and the pressure analysis. So we're given that A is equal to 3 feet, that's the only given, and again we're trying to find the depth D at which the gate opens without any external forcing, so without any help from a servo motor or DC motor, whatever. So the first thing we're going to do is show a free body diagram of the gate, and if we establish our water level right here, you can see that we have a symmetry above the water line such that we have atmospheric pressure acting on this side and atmospheric pressure acting on this side, both on equal surface areas. So these forces actually cancel, and we're not going to consider them in the analysis. If you go beneath the water level, you see that you have another subnet hydrostatic force, FH, which is basically the combined effects of the hydrostatic pressure acting on this face and the uniform atmospheric pressure acting on this face. So combining the forces from those two effects, you get FH. You have our forces on the hinge here, AZ tilde and AX tilde, and again, those are just the reaction forces from the hinge A. And again, you have another subnet force FV, which is the combined effects of the constant uniform hydrostatic pressure at this level and the constant uniform atmospheric pressure at this level. And combining the effects of those two forces, you get FV. And what you end up having here is the pressure on this face is actually constant because this face is at a constant elevation. And the pressure on this face is linearly increasing with depth because this face is not at a constant elevation. So you'll end up seeing a pressure distribution that kind of looks like this on this face that increases with depth, and the pressure distribution on this face will be a constant uniform pressure distribution, very similar to the constant uniform pressure distribution you see from the atmosphere on the opposite face on the same side. So what we end up wanting to do here is kind of establish what we mean by net pressure, and I kind of already went over that, but if you look at this orange dot here, you could see that on one side, on the left side, you have your hydrostatic pressure, so to speak, and on the right side, you have your ambient pressure, your atmospheric pressure, and they're kind of acting on the same little differential area dA, so the net pressure would just be pH minus P infinity, and you can see, again, as we mentioned, pH is a function of depth, it is a function of Z tilde. Now, if you look at this blue dot, which actually I don't have drawn here, so let's kind of draw out any arbitrary location. Let's draw right here. So what you end up having is you have your PV, or your pressure on this face right here, and you have your P infinity, or your pressure on this face right here. The ambient atmospheric pressure is acting downwards, and the hydrostatic pressure is acting upwards. And that's where you get this little diagram, and they're both acting on the same differential area dA, which is kind of represented by this blue dot. And what you could see is, as we mentioned again, PV is constant in this case because the pressure on this face is constant because this face is at a constant elevation. So PV is constant, and we've already assumed that P infinity is constant. The pressure analysis on this face ends up being significantly simpler than the pressure analysis on this face. So one quick note here, the buoyant force is equal to the net hydrostatic force in the vertical direction. So do not apply both Archimedes' principle and the hydrostatic pressure equation in Z. So in other words, pick either Archimedes' principle or pick the hydrostatic pressure equation, but don't use both, at least in the vertical direction, because the buoyant force is the hydrostatic pressure equation in the vertical direction. So in this case, we're just going to use the hydrostatic pressure equation. We're not going to use Archimedes' principle. If you were to apply both and apply them both in the vertical direction, you'd basically be applying the same equation twice. So now that we have that out of the way, what we're going to end up saying is when the gate begins to open, this contact force Fw, which is basically the normal force of the lip of the wall acting on the gate, will approach zero. So that contact force will approach zero when the gate begins to open. So as we go through our Newton's second law and our sum of the moments, we can end up zeroing out Fw. So it turns out that we actually don't really need the sum of the forces in x tilde or the sum of the forces in z tilde. We just kind of have those written out for habit's sake. So you'll end up seeing that we can use the sum of the forces in x tilde and z tilde to find the reaction forces at the hinge. We don't really need those in this problem. What we really need in this problem is the sum of the moments result, which shows that d1, or this distance right here, the distance from the hinge to fh, is equal to fv over fh times d2, where d2 is the distance from the hinge to fv. That result we will use, and that's just from this simple moment balance right here. What we end up needing to find next are the magnitudes of the subnet hydrostatic forces, so Fv and Fh, the combined effects of hydrostatic pressure and atmospheric pressure on the respective faces. So for Fv, which is the force on this bottom face right here, we end up seeing that it's just equal to P net times A. And again, we've gone over that P net is constant. It's just PV minus P infinity, which is P infinity plus rho g d, because d is the depth at which that face exists. This depth right here is d. So that P net is PV minus P infinity, which is P infinity plus rho g d minus P infinity. The P infinities cancel, and you end up getting rho g d times AW, where AW is that area A, the area of that face, that bottom face, assuming its width is W. So that's not too bad. FH is a little bit more complicated. FH is the force on this face right here, and this pressure increases linearly with depth. So what we end up needing to do here is we need to integrate that pressure over the face. So FH is equal to the integral over A of P net dA. Again, P net is P infinity plus rho GH minus P infinity. So you have the hydrostatic pressure on the left side here, this side right here, that's P infinity plus rho GH. And you have minus P infinity or minus the atmospheric pressure on the other side. That's the net pressure at any little differential area dA. And then we multiply that by dA, and that gives us our little net differential force. And then we integrate that over the entire area of that vertical plate A, over this entire area right here. And what we end up getting there is the total subnet force, so to speak. And one of the tricks with this integral here is you're going to end up getting rho gh, so the integral over A of rho gh dA. How do you handle this h, this little h here, which is just the depth from the free surface as we kind of have shown here? If you're at any little point, at any little differential area on this face right here, you can see that the h to that point is d minus its z tilde coordinate. So if we're looking at, say, this point right here, you could say that the h to that point is this depth d minus its z tilde coordinate. That gives you a positive number, because h is defined as positive. That gives you a positive number that describes the distance from that point to the free surface. So little h is equal to d minus z tilde, and that basically describes the depth from the free surface to any little point, to any little differential area on that face. So what we end up saying then is h is, as shown here, d minus z tilde. And at this point, you could split up this integral as shown here. And now what you could do is you could use first moments of area to simplify those integrals, or you could just perform the integrals. I just perform the integrals here, and we're integrating essentially by saying, hey, this dA, this little differential area dA, is equal to W, the width of the plate, times dz, a differential height in z along that vertical face. So W dz tilde is that differential area, and we're going to integrate from z tilde equals 0 to z tilde equals d, and that gives us the entire area of the plate. So what we end up getting here is if we perform this integral, we get this result right here. And that shows that FH is equal to the quantity rho g WD squared over 2. So one note here is d is considered constant because it is the depth at which the system is still just barely static. So at the point at which that gate is still just barely static, it's not moving, that depth d where it's just on the border of moving, where FW is just approximately 0, as shown here, that depth D is a constant. And so we're considering it a constant in these equations, which allows us to perform these integrals. So now the next question is, how do we find the locations of these forces, Fv and Fh, so D1 and D2 as we had in those diagrams? So the first thing we'll note is Fv, or that subnet force on the bottom plate, should act at the center of the PV distribution because PV is constant. So the pressure on that bottom plate, again, is constant. So the subnet force from that pressure distribution should act at the center of that distribution. Therefore, the distance to that subnet force, D2, should be A over 2, or the length of that plate divided by 2. So we're kind of positing that D2 should be equal to A over 2. Therefore, since we know that D2 is equal to A over 2, and we have an equation for D1, we could plug in D2, and this is, again, the result from the sum of the moments. We plug in D2 to this equation, and we end up getting that D1 is equal to A squared over D. And just rearranging that equation, we get that D is equal to A squared over D1. So this is an equation for the depth D. And we know what A is, we just don't know what D1 is. So to find D1, how do we find D1? Well, we need to equate moments. And what I mean by that is the subnet force on that vertical face should create an equivalent moment to the distributed pressure on that same face. So the distributed pressure on that vertical face creates a bunch of little differential moments that when summed together create a big macro moment, so to speak. And that big macro moment should be equivalent to the macro moment caused by FH on that same face. FH times D1 is equal to the integral over A of P net Z tilde dA. So what this is basically saying is take all the little differential moments on that vertical face and sum them up over the entire area of that face A, and that should be equal to the macro moment created by FH on that same face, right? And then we just need to find the D1, so to speak, the distance to FH that makes that statement true. And we could go through this whole integral. We've done this a couple times on the channel, but what we end up seeing here is, again, kind of similar tricks we saw previously, where we have this h, and again, we're calling h d minus z tilde, and you can kind of see that substitution here. H is d minus z tilde. But if you complete that integral as we've done in the past, you can see that fh times d1 ends up equaling the quantity rho gw d cubed over 6, this quantity right here. And then solving that for d1, just doing some algebra, you can see that d1 is equal to d over 3. Simply, d1 is equal to d over 3. So now that we have an expression for d1, which we got from equating moments on that vertical face, and we have an expression for d, which we got from the sum of the moments about the hinge A, we can plug this result from 3 into this result from 2, and we could find that d is equal to a times the square root of 3. That's it. D is just equal to a times the square root of 3. It's an amazingly beautiful and simple result. And what we end up getting is if we just plug in A is equal to 3 feet, we find that D, the depth D at which that gate begins to open, is 5.2 feet. That's it. It's just 5.2 feet. It's simply equal to A times the square root of 3. So the only thing left that I really want to show is kind of a proof of 3.1 here. So FV should act at the center of the PV distribution because PV is constant, therefore D2 is equal to A over 2. You could prove that this is true by equating moments in a very similar fashion on that bottom face. And I just have that quick proof here. Again, equating moments on the bottom face. So what we end up having is FV times D2 is equal to the integral over A of P net x tilde dA. Again, P net is rho g d in this case because we're looking at the bottom face. X tilde is the moment arm to one of those differential subnet forces at any given differential area dA. And then we have our dA. And if you perform this integral, which is in concept the same integral as we had in the previous slide, you'll find that FV times D2 is equal to the quantity rho g d WA squared over 2. And then solving for D2, you see that D2 is simply equal to A over 2, as we kind of intuited in the previous slide. Okay, so that should be it for this video. I really appreciate you watching. Thank you very, very much. And I will see you next time.